Kartik, can you see if the audio is good again?
Yeah. Yes, sir.
All right, nice. All right, I think we're gonna get started. We'll let people come in if they come in later. So today will be ML Monday lecture number 3. We're gonna be going over, huh? It's up to you. You can come here too if you want. You can just also sit by the edge there and see if people, yeah. So we'll be covering Jupyter, NumPy, Pandas, and Matplotlib. All 4 of these are Python packages, as we talked about in our dependency management lecture last week. And they're kind of core Python packages that are used in machine learning workflows. So we're going to go over them and have a code demo at the end to kind of see what they're like. So introductions, I'm Alvin Wong. I'm the education lead of GatorAI. And I'm joined by a few ML lecturers who will help me out throughout the semester, Kartik, Siobhan, and Srinikesh. And they'll go over some of the other lectures to help me out throughout the semester. As you may know, this is a beginner machine learning lecture series, right, with a focus on deep learning concepts, specifically neural networks. And this semester we're focused on applications, right, of these. You can contact us on any of our social media platforms, and we're going to have resources always on our link tree. We will probably have a GitHub up later of all of the Jupyter notebooks that we're going to be creating for this lecture series. So you guys can also go on our link tree after and look for our GitHub there. So let's start with the first Python package that we're going to be looking at, which is Jupyter. So Jupyter states that it's a large umbrella project that all centers around providing tools and standards for interactive computing with computational notebooks. So the main idea of Jupyter, right, is it's a platform for rapid development and testing of Python code, essentially. And they use what are called interactive computational notebooks for this. And this is different from traditional Python code, because when you're running traditional Python code, you kind of can run just your code and you have to run it over and over again if you want to see what it is. Jupyter Notebooks actually lets you store intermediate values and run your code again. As well as that, it allows you to have text, images, and a lot of different things displayed in your notebooks as well. And it's all contained within that individual notebook. So if you have images and text and stuff and documentation in your notebook, you can actually give it to somebody else and they can run through it themselves and they can see all the results, which is really, really good, especially when you're in a research environment or something where you need to share your code and work on it with others who want to see your results in kind of like an image format, right? So like I said, a notebook is an interactive document, lets you write and run code together with explanations, equations, and visual outputs. This is also something that's very key that I forgot about. It uses a specific designated virtual environment. Remember, we talked about in our last lecture, right, that the virtual environment separates your Python packages, right? And this is really important because Jupyter Notebook lets you designate which virtual environment you're using, of course, and also lets you designate which version of Python you want depending on which virtual environment you use, which is really beneficial for machine learning when you're working with different library versions and you're working with different Python versions. Next is the NumPy. So you guys probably have heard of NumPy. It's one of the more popular Python projects. So it's an open source project that enables numerical computing with Python. The biggest thing about NumPy is it implements a specific data structure called the ND array. And essentially what it is it's essentially an optimized array. So in Python, there's lists, which is the standard array-like data structure. NumPy arrays are a lot faster, but they do come with some assumptions, such as the array is homogeneous, right? You can't have multiple data structures in your NumPy array. It all has to be a single data structure, which is different from Python lists. In Python lists, you can have ints, floats, whatever, in a single list at once. And so NumPy also adds a lot of support on top of these NumPy arrays, right? It adds customized support for multi-dimensional arrays and matrices and functions on these data structures. And most of these functions are implemented in compiled C++ or C or Fortran code, right? And this is really important because in Python code, even though lists are technically implemented in C, a lot of the functions on lists are implemented in Python. So the summation, for example, if you were to try and sum a list of integers in Python and you were to run the standard sum function, it would run that in Python actually. But if you were to run numpy.sum on a NumPy array, it would actually run that in C code, and so it would be a lot faster. And this is one of the reasons why NumPy is used primarily, is because it's just so fast, and when you're working with machine learning and stuff like this, you want things to be fast and not take as much computational resources, right? So like I said, it integrates code from C, C++, and Fortran code, and it basically makes it accessible in Python. So in Python, you basically just call the NumPy functions, and NumPy calls the stuff on the back end for you. And it's faster than regular Python lists, and even the standard library arrays for multiple reasons, which we've covered. And we can see on the right-hand side here some of the use cases of NumPy, right? A lot of statistical and arithmetic operations, and there's a lot of other different things that we'll be going over in our code demo. And NumPy is really just used in a lot of scientific computing where you really need to be analyzing data extremely quickly. So next we'll be talking about Pandas. So NumPy, right, is about numerical computing. Pandas is all about data analysis, storing your data, and being able to query your data in efficient ways, right? So Pandas describes itself as a fast, powerful, flexible, and easy to use open source data analysis and manipulation tool. And of course, it's built on top of the Python programming language, which is why we included it here. So it's an open source Python library for data analysis and manipulation. And so NumPy introduced the NumPy array, right, which is its main thing, right? Pandas introduces two things, which is the Panda series and the Pandas data frame. And the Panda series is essentially a list of elements, right? It's similar to a list in Python, except that it has additional functionality on top of it. A Pandas data frame is essentially like an Excel sheet, or what you might think of as an Excel sheet. It has rows and columns, and you can label your columns. And so essentially you can perform a lot of standard data operations and data analytic operations that you would on, say, an example like an SQL database or something like that. You can usually implement it in some way on a Pandas data frame. And Pandas data frames are used throughout a lot of different Python environments, and especially in research, Pandas is used a lot for manipulating data and also storing it and using it extremely efficiently. Some things to note about Pandas is that it's built on top of NumPy. So this is the reason why NumPy is used so much, is because NumPy is fast, and obviously Pandas needs to be fast. It's designed for working with structured and tabular data, right? So think of things like CSVs, Excel sheets, stuff like that is what tabular data is, right? And it's a core tool in data science and machine learning, obviously, because it's used to store a large amount of data that you often want to use when you're training your models. The next and final library that we'll briefly talk about before we go into the code demo is Matplotlib. So Matplotlib is a Python package for creating graphs and charts, right, out of your data. It says that it's a comprehensive library for creating static, animated, and interactive visualizations in Python. Matplotlib makes easy things easy and hard things possible. And that's very true if you know how to use Matplotlib. It's extremely strong in creating a lot of different graphs, 3D graphs, interactive graphs, and things that you can work with and analyze your data in a different way. And it's used, of course, in a lot of research environments and stuff like that to kind of get a better idea of what's happening with your data. So Matplotlib is a Python plotting and visualization library, right? It's most commonly used one of the most commonly used, I should say, for data visualization in Python. There are other examples such as Seaborn. Seaborn is like a competitor almost of Matplotlib. It's also like a a chart creator for Python, and a lot of people use Seaborn as well. But Matplotlib has kind of been around longer, so it's kind of been the de facto for a while. Matplotlib obviously works with NumPy and Pandas data, and we're going to be showing that in our code demo today. And it kind of just shows how all of these libraries usually work together in a machine learning development setting. And it's also integrated with Jupyter Notebook. We talked about how Jupyter Notebook can like show images and equations and text and stuff like that. So Matplotlib is actually integrated with Jupyter Notebook so that when you create Matplotlib images, they actually show up directly in your Jupyter Notebook, which of course is very useful when you're sharing these notebooks with others. So now that we've kind of gone over a brief demo of this, we're going to have a code demo, right? So I have my shell set up. So first of all, we're going to get started with our virtual environment. And if you guys have a laptop, you guys want to follow along, you can. So first, we're going to use Conda. You can use any type of Python package, Python virtual environment that you want, but we'll use Conda just for this case. So we're going to create first our virtual environment. We're going to We're going to create it, and the nice thing about Conda is we can specify the Python version. So we're going to specify Python 3.11, and we can see here that we actually do get Python, the exact version that we want, right, which is nice. And that's really important, as we've said, when you're working with different Python versions, because, of course, that changes all of the dependencies you want and stuff like that. So we're going to create our Conda environment. Now we need to activate it, right? Because we want to add some of our dependencies that we've mentioned before. So we'll activate our Conda virtual environment, and we'll install the libraries that we want. And these are the names for them. You can always search them up like online on the PyPy package index, right? Or the Conda package index. You can always find them there, and they'll give you the exact commands that you need to type in. Usually, you probably won't know these all off the top of your head. So let's first start off with Matplotlib, and we'll see that we can download it, and we see that we're getting a bunch of transitive dependencies, right, that we talked about in the last lecture, and these are all going to be added to our environment as well. So next, we'll install NumPy. We'll get NumPy, because Matplotlib already includes NumPy, and so we're going to install Jupyter, right? So Jupyter is our platform that we're going to be using for the development and testing of code, right? So we'll install all of the Jupyter packages that we need. And then let's see, what else were we missing? I think we're missing Pandas. Install Pandas. And the volume is so loud. All right. So we'll get Pandas, which is our last package that we need. All right. So the next thing we need to do is that I told you that Jupyter allows you to designate a virtual environment, right? So this is one of the most important things, right, about Jupyter Notebooks, is that it lets you define what kind of Python version and what runtime you want and what packages you need. So we have to connect our virtual environment to our Jupyter Notebook. So the way we can do this is we just do Python. And you can search up the commands for this. Like, this is stuff that really you will almost never memorize the commands for, but we're going to set this up right now. So we have lecture 3, and essentially what we're creating is called a kernel. And a kernel for Jupyter is essentially just the runtime environment that has all of the packages and things necessary to run your code. So we can see that we created a kernel based off of our virtual environment. And we can see here that we created the kernel spec lecture 3 in Jupyter because we've installed Jupyter, right? So now that we'll do this, we can run Jupyter Notebook. So Jupyter Notebook is just the command to start up a Jupyter instance, right? And we can see exactly how we can start developing using Jupyter, right? So it's going to run us all this stuff. And the core thing is to access this, the server, open this file in a browser, right? Or any of these. So we'll just open it up. And this is what you'll normally see This is called Jupyter Notebook, right? And it's essentially the platform that we're going to be using for the testing and development in many cases. So we'll open up the notebook that I've created already, and we can see here that this is our kernel. I had a test kernel that I created before, but we can also see that we have Lecture 3 kernel, right, which is the kernel that we just created that was created from our Conda virtual environment that we just created, right? So our kernel will now be used to execute all of the code, and our kernel also will connect us to all of the dependencies that we just installed right in our Conda environment. All right, so we're gonna go through the NumPy, Pandas, Matplotlib, right, our tutorial, right? So obviously we've installed all of the dependencies, right, that we have. So we're just gonna check first, and we're gonna see, do we have all of the dependencies? So we're gonna import all of our Python packages, and we can print the versions of the Python packages here. So we can see NumPy, what version we have is 2.42. We can see Pandas 3.0.0, and Matplotlib is 3.10.8, right? All right, so let's get started with some of the fundamentals with NumPy, right? So like I said, NumPy provides the NumPy array, which is one of their core features. It's a fast, memory-efficient, n-dimensional array with vectorized operations, and it's ideal, obviously, for numerical computing, scientific computing, and data preparation, where speed is key, right? You're not trying to run through your data all at once and have it take, days, weeks, months, right? So first of all, let's talk about how to create NumPy arrays. There are many ways to create NumPy arrays. You can create them directly from Python lists, right? Because Python lists and NumPy arrays are very similar. We can create them from NumPy functions, right? So NumPy allows you multiple functions to create arrays, such as arrange, linspace. We can also have NumPy arrays that are created with initial values throughout the entire NumPy array, and we can also have random numbers. So let's go through each of the lines and explain them. So here we can see that we have a Python list within here, which is just 1, 2, 3, 4, right? And we can pass it in as an argument to our NumPy.array function, right? And we can initiate or instantiate a NumPy array. We can also have the arrange function, which is also another way to create it. And we pass in 3 parameters to the arrange function. We pass in the start position, the end position, as well as the step size. Actually, I'm going to clear all of the outputs, so that way you guys cannot see what happens before. All right, there we go. Yeah, and so we can see that Jupyter allows you to see the outputs of all of your code as well, which is really nice, which is what we want. But I don't want you guys to see too much, so that's why I got rid of it. All right, so numpy.linspace is similar to arrange, except what you do is you provide the start, the end, and the number of points that you want to sample from this range, and then it'll linearly sample the number of points in between, right? So we have 5 points that we want to sample in between 0 and 1, so we'll get 0, 0.2, 0.4, 0.6, 0.8, 0.1, right? We can also do mp.0, so this just creates a multi-dimensional array filled with zeros, right? And what we're passing in as an argument is the dimension of the multi-dimensional array that we want to create, right? In this case, it's 2, 3, right? And if you remember from linear algebra, rows, columns, so in this case, it would be analogous to that. But in multiple instances, we have more than 2 dimensions within our multi-dimensional arrays. And we'll see that here. And same thing with mp.ones. We're going to create a multi-dimensional array with 2 rows and 3 columns filled with ones. And we can also create full. So once again, we're going to pass in the number of dimensions as well as the number that we want to create. So this is just going to create a multi-dimensional array with 2 rows, 3 columns, and it's all going to be filled with 7s. And of course, we can also use RNG, right, random number generator, to generate our multi-dimensional array for us. And we can just call RNG.normal here. We define the center, right, of our distribution, define the standard deviation, which is 1 in this case, and we also indicate the size, right? So every single value in our multi-dimensional array will be pulled from this probability distribution, right, with mean 0 and standard deviation of 1, right? And then the nice thing about Jupyter Notebook is it displays the results of the last line out for you, so you don't need to print anything or display anything. It just gives it to you. So we're going to run this, and we can see the output of our code, right? We have the NumPy array, which is A, and that's 1, 2, 3, 4. We have the arrange, right? We can see it goes from 0 to 10, right, with the step size of 0.1. We have the np.linspace, and I'm actually wrong about it. We have 0, 0.25, 0.5, 0.75, and 1, right, because 5 is the number of points we're sampling, so I would have given 1 extra point on mine. We have the zeros, the ones, the full, and of course we have the RNG, right? So that's how we instantiate NumPy arrays. So now we get some information. Let's say you have some NumPy arrays and you want to get some information. We have a question.
Yeah, sorry. Is range exclusive of the last, but linspace isn't? Is that why it doesn't go to 10 for the? It goes from 0 to 9.9.
Yes, that is right.
Linspace will always include that last value?
Yes. Linspace will always include that last one. Our range is very similar to like for I in range 0 to 10 in Python, right? So it'll never reach that last one, but it'll start there. But linspace is inclusive for the start and the end. All right, that's a good question. All right, so next we want to maybe get some information about our arrays, right? So let's say you're passing an array and you had to do some debugging. We can call .shape on it, right, which is an attribute of any NumPy array. We can also tell you the D type, which is the data type within the NumPy array, because remember, NumPy arrays are homogeneous. They only contain a single data structure right within themselves. They are not like Python lists where you can have multiple elements or multiple types of elements within them, right? And we can also reshape it, and we can change the view of the data when possible without copying. And the beautiful thing about this is it's all done for us in compiled C, even the reshape, which is really important here, right? So let's run this code. We're going to have x equals np arrange, right, to 12. And then we're going to reshape it to have 3 rows and 4 columns. And we'll see what we get when we actually reshape it, right? So you can see np.range is exactly what we want it to be from 0 to 11, right, because 12 is excluded. And we'll reshape it to have our 3 rows and 4 columns, right, which is exactly what we want. We print out the shape, which tells us that exactly has 3 rows and 4 columns, and it tells us the data type within it, which is int64, right? And we can see here that if we were to change this and do 3.5, that it would give us an error, right? Because obviously the original NumPy array of x has 12 elements within it, and we can't reshape it into something that contains 15 values, right? So it's not allowed. So we have to reshape it into something that's actually feasible, right? So indexing and slicing. So NumPy allows slicing and indexing similar to Python lists, right? And returns a view, not a copy of the NumPy array. So we can see here that we're doing the same thing. We're going to get a range, and then we're going to reshape it into what we want. And then what we're going to do is we can look at the first row, right, which is obviously the first element because this is a multi-dimensional array. We can look at the second column, which is where we take every single row and take the second entry in that row, which gives us the column. And we can also get a submatrix, right? So we can specify certain bounds and get a submatrix of the original matrix. As well, we can also do Boolean masking on our NumPy array, and so we can see exactly what we get here when we run this code, right? So we get our original NumPy array, which is just our 1, 2, 3, 4, right, with 3 rows and 4 columns. We get the first row as we expected. We get the second column as we expected. We get the submatrix, right, that we wanted from taking in these indexes. And then we can even get our Boolean mask, right, that shows is each element in x2 divisible by 2, right? And so we can get that here, and we can get even the even values based on our Boolean mask. So this is really, really strong because NumPy does this extremely quickly, and as well, a lot of these features are not really implemented in Python lists, right? In Python lists, you would have to actually write the code yourself to check every single element in that list and do it for it. But in NumPy, you can access every single element individually using a function, and these functions are vectorized, right? So they're implemented in C and they're run in parallel, while in Python, this is not allowed. All right, so next we'll talk about broadcasting and vectorization. So broadcasting is a feature in Python where you can apply operations between arrays of different shapes. And this is really, really important. It's one of the bigger reasons why NumPy is faster than just Python list, is because these operations run in compiled code, right? Instead of Python loops. So if you were to try and do these same transformations on Python list, you would have to write some Python code to glue everything together, and that would be really slow. So we're going to define our NumPy array, right, with 1, 2, 3, and we're going to define a constant integer 10, right? And we can see here that we can actually add the constant b to every single element, element-wise, to a. And so what we expect to get out of here is an array with shape 3, comma, and then there's nothing there, but it's like three dimensions and then 1, right? And so we can print the result, right? So this is a one-dimensional array, and we should expect that the 10 is added to every single element in A, right? So A plus B should end up becoming 11, 12, and 13, right? In Python, once again, you wouldn't be able to do this type of broadcasting. You would have to iterate through every single element in the Python list to add it, and that's a lot slower because you're running that code in Python, not compiled C, right? Which is important. So for our broadcasting example number 2, we can even make it a little bit more complicated, right? We can take an array of 5 elements, right? And we can take another multi-dimensional array that has essentially what is just columns here of 10, 20, and 30, and we can actually add x and y together, even though they're essentially completely different array shapes, right? And we can get the result, and we'll see exactly what we get here. All right, so for our first broadcasting example, right, we have A, we have B, the result shape is 3, and we get 11, 12, and 13, right? And we can add those. For the broadcasting example number 2, we have X, which is just, right, a one-dimensional array, and Y is a two-dimensional array with essentially just one column, right? And we can add them in such a way that we get this 3 by 5 matrix, right? This 3 by 5 multi-dimensional array, right? And it does this, like I said, all in C. So this is one of the reasons why NumPy is much faster and used compared to Python, especially for types like machine learning and stuff like that. We can also do reductions as well. So here we are generating a bunch of random integers, right, with 4 rows and 3 columns, right, where our mean is 0 and our standard deviation is 10. So essentially we expect it to be a one-dimensional array, right? And we can actually, not a one-dimensional array. We expect it to be a multi-dimensional array, like I said, of 4 rows, 3 columns. We can sum all of the values, right, in the multi-dimensional array, but we can also sum it based on what is called the axis. And so the axis allows us to define which direction we want to produce the summation, right? And I'm going to run it here so we can actually see what's going on, and so we can explain it, right? So we can see what M is here, right? It's 4 rows and 3 columns, right? Shape 4, 3. The sum of all elements in M is 52, right? And the sum per column along axis 0 is the sums here, which is 18, 21, and 30. And we can quickly verify, right, that if we were to do the summation of 5 plus 9 plus 0 plus 4, right, that we would get 18. And we can see that we can think of the axis as what kind of, which kind of shape along here that we're removing, right? So axis equals 0, we can think of this as removing the 4 rows or grouping the 4 rows, and then we're summating by the 3 columns that we have here, right? It's similar for axis 1. We can think of getting rid of the the second value in the shape, and then summating along the rows here, right? And we can see that's exactly what I get, right? And so especially when you're working with more dimensions than 2, like maybe you're working with 3-dimensional arrays or even higher, working along the axes can be a little bit unintuitive, but this is kind of to help you see exactly how we're doing the summations by. All right, so now that we have NumPy fundamentals out of the way, let's talk about Pandas. So like we talked about, Pandas provides you with series and data frames, and it's built on top of NumPy, right? And so we're going to see exactly how we can do them. So we can define series in many different ways, right? And data frames as well, but we're going to show you two simple ways to manually code them, right? So you can use essentially a list and an index provided to a series. And for a data frame, you can use a Python dictionary, right, to create a data frame. Later, we're going to show you more common ways that you would normally pass in information to create a data frame. All right, so we can see here what our Pandas series, put a new line here, right, where it's essentially just a series, right, where we have the columns and we have labels for the rows, right? A data frame, like I said, you can think of it like an Excel sheet. So here we can have the columns, which are name, age, and city, and we have the rows, right, which are the entries, right? And these are the row indices, right? You can see here. So normally, what you would do is you would read in data through either a CSV or a JSON file into a data frame. But to keep the notebook self-contained, we're essentially going to create a CSV or hard code the CSV, right, as a doc string, and then we're essentially going to read it in. So let's read in our makeshift CSV that we've defined here, and we're going to display it. So we can see here it looks exactly as you would expect it to. We have our columns, which are date, store, product, units, and price. And we have the different rows that we've defined here, right? And we can see here that we get essentially what is a table. So this table is defined as a Pandas data frame, and Pandas has a lot of different functions for us essentially to perform data analytics on this data frame, right? So inspecting data is the first thing you normally want to do when you load data in through either online or some other way. So we can display the head of the data frame, and we can also call .info on the data frame. And essentially, .head it provides us with the first 5 rows of the data frame to inspect and make sure that everything kind of should be as we expect it to, right, which makes sense. We can also pass in a different number. So we can pass in 2, 3, 4, whatever we want, integer we want, to display what the amount of rows that we want. And the default is 5 here, right? The next function that we want to use is sales.info. So that returns us essentially all the information, or a shortened condensed form of the information of what we want, and this is what we get. It tells us, right, that it is a Pandas data frame, tells us the range index, the data columns, total of 5 columns, and it gives us a nice summary of everything, right? So one of the things that we can see here is that the columns all have their own individual data types, right? So date has a date time data type, store, product have string time data types or string data types, units have float 64 data types, as well as price does. And it also gives us a nice little thing of the non-null count. And this is really important because in data analytics, right, most of the times your data set is going to be very noisy. You're going to have missing values, NaN values, a lot of stuff that doesn't make sense. So this lets us see here that we have a non-null value, right, in our units column. And if we actually go up, we can see here, right, that is defined as NaN, right? So there is some data missing in our makeshift data set. We can also do sales.describe, right? Once again, sales is our data frame, and we're calling the describe function on it, and essentially gives us a list of statistical information about our columns that can be described, right? So for example, store and product obviously are strings, so there's no really statistical analysis you can do here, but they can do a statistical analysis on the numerical columns, right? So we can see here that we get the count, the mean, the min, the quantiles, right, of our units and price, the max, as well as the standard deviation, right? And that just gives you also a brief idea of what's exactly happening in your data frame. Because right now it's really easy for us to just essentially print out our entire data frame right here and see everything that's happening. But when your data frame is 100,000, you know, a million rows, you know, sometimes even like a billion rows, there is really a lot to see, and you can't go through it all, right? And so these ways allow you to kind of gain some understanding of what's happening in your data. Okay, there's also selecting data columns, right? You can do .lock and .ilock. .lock is essentially by Boolean filtering or by, it's by Boolean filtering. .ilock is essentially getting the rows based on the indices. And then we can also do column selection by just treating the data frame as a dictionary and querying by the column name as if it were a key, right? So we can see here that when we do display of the sales of the product, what we get is a Pandas series, and we essentially get all of the products, right, based off of our original data frame, which is right here. We also can display the sales, right, the rows from 0 to 3, and we can see that we get that here. And we can also do Boolean filtering with .lock. So we can do a conditional here, right, and essentially is we want all rows where in our sales data frame, we're looking for where the sales store equals east, right? And so we can return that here and we can display east, and we can see that we get all rows where the store is labeled east, right? So this is also really important for looking at different stuff and kind of analyzing your data. Missing values. So Pandas allows you to get rid of a lot of your missing values, right? You can do, you can specify custom functionality for what you want to do with NaN values or missing values. In machine learning, it's often advised that you have a good approach to kind of dealing with this sort of stuff. Most of the times what you'll do is you'll either remove them or you'll do interpolation. So you'll take the most common value or you'll have a default value for that missing value. And so that's kind of what you do. So in this case, what we're going to do is we're just going to replace the NaN value with a 0, right? And then we'll label it as sales clean. And we can see here we've removed the NaN value and just replaced it with a 0. We can create new columns easily, right? Just like NumPy, we can perform, essentially what is series by series functionality. And so we can classify or create a new column called revenue, right, where we multiply the Pandas series of units and the Pandas series of price, and we get our new data frame essentially, right? And we're defining the new column here. We're going to skip group by because we are running out of time, and I want to make sure that we not go over time here. So we're going to get started with Matplotlib fundamentals. So like we said before, Matplotlib is a plotting library for Python, and there's two styles of Matplotlib. You can either do PyPlot, which is the stateful interface, and it's generally easier to use. And there's also the object-oriented interface, which is a little bit harder. It's more explicit though, and it's more scalable, and it's used for more complex graphs. All right, so PyPlot basics, which is the easier one, the stateful interface. Essentially, we just have this plot, and we can essentially just define things for us. It defines things for us, and we can just essentially plot exactly what we want. So we define NumPy arrays, right, which we're going to use as our data. So we're doing a linear space here with 200 points. And because we're doing NumPy, we can call a function on that NumPy array and get a new NumPy array, right, which is essentially just the transformation, which is the cosine of x, right? And so essentially what we do here is we create our plot figure. We plot x and y, right? It does it for us. We just create the title, the label, and we can just show our plot, right? And we can see our cosine here. It's very easy to create, and there's not really much that goes on. Most of the times you'll be looking at previous people's, Matplotlib graphs and kind of just taking from there. The object-oriented interface, you explicitly control the figure and axes objects, so there's no plot object for you to manipulate directly. So here is the same thing, right? Except now we have two lines that we want to show on our graph, right? And with the object-oriented interface, we can do this a lot more easily. So we essentially, instead of having plot, we do the figure and the axis. And we can think of the axis as the actual graph, and we can label multiple things on it. So we can plot on the axis, we can plot the x and the y1, right, which is the sine of x transformation. And we can also plot x and y2, which is the cosine of x transformation. And so essentially what we can do is we have a lot more leeway, we can set the title like we did before, as well as the X label on the Y label, and we can show our plot here. And so we can see that we can have multiple lines right on this, and that we get a lot more fine-grained control with our object-oriented interface approach for Matplotlib. All right, now we have scatter plots. So scatter plots are also implemented in Matplotlib. There are a lot of other plots as well that are implemented, and we'll go over some of them. So we're going to generate some random points, right? Like before, we're going to generate some random points using RNG. We're going to generate 400 random points. And essentially what we're going to do is we're going to generate a semi kind of linear transformation, right? So we're going to multiply x by 0.5, which is our linear transformation. And we're going to add some noise to our y values, right? Essentially is what we're doing. And essentially what we're doing is we're going to show our scatter plot on the figure. So we do subplots, we do a scatter plot here, and we can show our scatter plot, and we get kind of what we expect here, right? With our scatter plot, and we define the color using this color gradient based on the x and y values. And we can see here that we get a scatter plot, and of course, a lot of these functionalities where it's like coloring and stuff like that, and legends are implemented in Matplotlib. There's also things like histograms, which I'll go over quickly, right? You essentially just call histogram on the axis, and you can create a histogram of a normal distribution, stuff like that. You can also create multiple plots, which are called subplots, right? And this is where you'll really need the object-oriented interface. So here, what we can do is we can create two plots right below each other, which is sine x and cosine x. And how we do this is by calling directly on the axis object. So this would not be possible using the stateful interface that Matplotlib has because we're directly interfacing with the axis, right? And of course, you can always save these plots as image files as well. You can save them as PNGs, PDFs, whatever you want. And we can see here that we can create like a damped sine wave, right? We just essentially multiply it by a negative exponent, right? And we're going to have a damped sine wave. And we can see here that we've actually created it and we've saved it as a pinch file here. But anyways, I think we're just under time, which is good. So that's good. And I think we've covered everything. So we're going to go back to the sign-in page. So thank you guys very much for coming out and watching. Please sign in if you guys have not already. I hope you enjoyed this lecture. And I know we kind of went over everything kind of quickly, but as we go through the rest of the lectures this semester, we'll make sure to kind of go through everything again and make sure that we're not going too quickly for this stuff. But anyways, I think that should be it for the lecture today. Thank you guys very much for coming out.